Hi, class. If you feel good about giving this hydrogen deficiency a try, pause the video, give it a try, and then we can work it together. If not, let's do the first one together, and then I'll let you try the second one. All right, so the first thing we want to do is look at our formula. All right, so we're going to come over here. And the number that you're going to want to pay attention to is that 7. Right? And same thing if you're looking forward to the bottom one, it's going to be that 6. That's where our href is going to come from. So if you don't mind, I'm just going to scroll back up for 1 second. The first thing we want to do is set up this equation here. All right, so we're going to take this equation and our href, we're going to use those 2 numbers I just highlighted. H molecule is going to come literally straight from the molecule. All right, so let's keep this formula in mind. H is 2n plus 2, and so that's going to be our href. All right, so let's do that over here. So I'm going to write it up here at the top just because we'll use it for a couple of our problems. So 2n plus 2. In this case, remember, we're going to use the 7. So we'll plug the 7 in. So it's going to be 2 times 7 plus 2 equals 16. All right, so if we're setting up our formula, our href is going to be 16 minus, and now we want to put a parentheses just in case we have a couple different of those formulas, right? Where we have to add halogens in or account for them, or if we have to account for the nitrogens and phosphorus. All right, so now our next number is we want to take that right from our molecule, so that 14. So we'll put our 14 in here. And then if we look at this, we don't have to do anything for oxygen, so we're actually all set. So I'm going to go ahead and erase this parentheses because kind of makes it silly to do it if there's nothing there. So now it's going to be in parentheses because we want to do that first and then put this all over 2. And so 16 minus 14 is 2. So 2 over 2 equals 1. All right. So not too bad, right? So this would tell me that I have at least 1 ring or 1 double bond. Right? You can't have both because we don't have 2 hydrogen deficiencies. So that's the other information it gives you is we can't have a triple bond in our molecule because that would require 2 hydrogen deficiencies. All right, so if you haven't done the second problem, pause the video, give it a try, and then we can look at it together. All right, so hopefully this is starting to get a little bit easier. So let's try this one together. So again, we're going to use the formula up here, 2n plus 2. I'll do this one right up on the top of this page here. So we're going to do 2. And now we're going to plug the 6 in for my n value plus 2. So 2 times 6 is 12, plus 2 is 14. All right, so we set up our formula. href is going to be 14 minus, and now remember the next number is the hydrogens right from the formula. So we'll take the 6. And then we want to see everything else. The oxygen, remember, is easy. We just ignore it. Nitrogen, we subtract 1, and we subtract 1 for every nitrogen. So this becomes minus 2. So I'm going to put that parentheses, and then I'll put the bigger one on top. And then remember, we divide this by 2. All right, so if we change this number, 6 minus 2 is 4. So 14 minus 4 is 10 over 2. All right, so then if we go forward, it's 5. All right, so 5 means that we have 5 hydrogen deficiencies, and so it can actually be a ring, a double bond, or some combination. All right, so as we're looking at this, that's going to give us insight into our molecule. And so what this molecule actually has is an aromatic ring. And let me just show you that just to kind of give you some context of what this hydrogen deficiency means, or H deficiency. Is if we look at this benzene ring, we're going to get 1 hydrogen deficiency for the ring, and then we get 1 for each double bond. Okay, so if we have 1 for each double bond, that means that this actually has a hydrogen deficiency of 4. So that means we still have one more in our molecule. And typically what this molecule looks like is it has an aromatic ring, and then it has another group outside of it. And so if you're thinking about the different groups, you want to think about, well, what would have another hydrogen deficiency? And so what this is going to actually look like is it's going to have a carbonyl in it as well. And so if we look at our carbonyl, and I'll draw the whole molecule together. It looks something just like this. And so your hydrogen deficiency comes from one double bond here. Okay. So that's 1, 2, 3, 4, and then the ring makes 5. All right. And so that's kind of that idea behind this, right? The one up above, the acetate, has an ester in it. And so we're thinking about the same. When we had an ester, we're going to get 1 from that double. Right? And so that's what we just want to think about is what information is this going to give you for the molecule? Let's try one more. So a lot of times we'll use this hydrogen deficiency in combination with IR, NMR, some kind of spectroscopy, right? So you go into the lab, you'll take your spectroscopy of the molecule, and you'll get some information. And so you want to start putting the pieces of information together. So it's almost like you're a detective and you're trying to solve for this molecule. All right, so what I would do first is whatever spectra you have, whether it's an NMR, IR, mass spec, you want to look for the information that's in there. So if we're looking at this molecule, there's going to be an OH buried in here. There's some CH stretching here and a carbonyl peak. Now, we're going to use that information plus our hydrogen deficiency to figure out which one of these molecules we have. All right, so let's do the same thing we did before. I'm going to shrink this down a little bit just to create some room. So we're going to have our href is 2n plus 2. And so remember that number is going to come from that 7. So if we do our href, it's going to be 2 times 7 plus 2. And so that's going to give us 16. All right. So now if we do the same thing as we did before, and if you don't mind, I'm going to jump around and kind of use this empty space here at the bottom. We're going to actually do 16 minus, and then don't forget that that actual molecule is going to give us our hydrogens. And I'll keep it in blue so it'll hopefully help us keep track of where that number came from. So there's our 10. Now this one we have halogens. And so if you remember, we're going to add the halogens, and I'll actually make these in different colors. So hopefully it's going to make it easy to see where the numbers came from. So for each halogen, we add 1. And so since we have 2 halogens, we'll add 2. And then remember with the oxygens, we do nothing. So we'll close our parentheses. And then we always divide this by 2 because it took 2 hydrogens to make 1 hydrogen deficiency. So now we do the numbers in the parentheses. So 10 plus 2 is 12. 16 minus 12 is 4. So 4 divided by 2 is 2. So now, if we come back up to these molecules, so look at these 4 molecules here, we want to decide how many hydrogen deficiencies each of these molecules have. So we've done the formula, and now let's look at the picture and tell me how many hydrogen deficiencies it has. All right, so if you want to pause the video and either figure out the hydrogen deficiencies of each of the molecules, or just tell me which molecule it is, I think that'd be great practice. If not, we can do it together. All right, so let's go through these. The first one, you want to look for any ring and any pi bond. So this has 1 ring and 1 pi bond. So this is going to have a hydrogen deficiency of 2. All right, we look at the next one. 1 ring, pi bond, pi bond. So this one actually has 3. Okay. Next one, double bond. All right, so that's 1 hydrogen deficiency. The ring is the second one. Someone gives me 2. And then if we look at this one, there's only the double bond and no ring. So this one has a hydrogen deficiency of 1. All right, before we even try to pick our molecule, this told me that there has to be a hydrogen deficiency of 2. So I can go ahead and already cross off anything that didn't have a hydrogen deficiency of 2. So it can't be you, and it can't be you. All right, so that helps. Right? And so I think if we look at the 2 pieces of information, you have to have a hydrogen efficiency, an OH, and a carbonyl. This doesn't have an OH, right? It has my carbonyl, but no OH. So the only one it can be is this one. And so that's kind of how we put the 2 pieces of information together. We're going to pull information from our formula to get our hydrogen deficiency, take our spectroscopy, whether it's NMR, IR, mass spec, pull out any information we can, put the 2 together, and figure out what the molecule is. All right, so hopefully that was helpful and kind of ties it all together. All right, the next thing we're going to do is naming. And the nice thing about naming in organic chemistry is it really follows a nice pattern. Right? It's going to keep doing the same thing over and over that we did for alkanes. And we just add a little wrinkle each time. All right, so what we've done with naming is we're always going to find the longest carbon chain. The difference now is it's got to be containing the double bond. Right? So it's the longest carbon chain that contains the double bond. And the other biggest thing is we want to give the double bond the highest priority. So we're always going to number from the side that gets to the double bond the fastest. Now, if you look down at the bottom, one thing I want to highlight is if you think about this first statement, I think in previous chapters, when you learned about alkanes and naming them, we really harped on you got to find that longest chain. And so on the one on the far right is kind of the best example of that. So you can go 1, 2, 3, 4, 5, 6. Let's see, you're probably saying, Jimmy, you've been telling us we also have to find the longest chain. Why does the example below say in red that we should get these 5 carbon chains instead of having the 6 carbon chains in blue? Because you always said it's the longest chain. It's got to contain both carbons as part of the double bond. All right, so on these examples, they all have the carbon being 1. It doesn't have to be 1, but it definitely has to go through that carbon chain. Okay? And so that's why this will be a substituent and can't be the parent chain, because it doesn't go through the double bond. We could have gone through the double bond and up, but then that would be a shorter chain. So if we're going through the double bond, we still want to find the longest carbon chain that has the double bond. All right, so let me erase the ones in blue so it doesn't confuse later. And then when you're picking the number that's going to tell us where the double bond is, you always pick the lowest of the 2. Right? So it doesn't have to be 1, but it's got to be the lowest number. All right, and then after that, everything else stays the same. We're going to name all the substituents. We're going to put the location and number of each of them. And then the last part of this is we're going to change the parent chain to have ene. And that's what's going to tell us our double bond. Right? And then we're just going to put a number in front that tells us where that double bond is. All right, so let's try a couple. So try this one. And let's do one more. All right, so let's try those 2 problems. So go ahead and pause the video, give it a try, and then we'll do it together. All right, so hopefully this went well. So let's start with the one on top. You want a number from the side that gets to the double bond the fastest. And remember, now the double bond has the highest priority. So previously we would have started on the left to get to that methyl group faster. But now we want to get to the double bond the fastest. So we'll start on the right and we'll go 1, 2, 3, 4, 5. So we're going to have 5 carbons. We have this top group, which is a methyl. We're still going to use the number, right? So it's on carbon 4, right? So since it's on carbon 4, it'll be 4 methyl. So let's put this together. So it's 4 methyl. And then we want to give a number for where that double bond is. So we're going to pick the lowest number, so between 2 and 3. Right? So it's going to be on carbon 2. So it's 2, and then 5 carbons is pentane, and we change it to pentene, right? Just like below. we're going to change the ane to an ene to show us there's a double bond. So it's 2-pentene. Right? And then just like before, the 2 in the ene is telling me where that double bond is. So it's 2-pentene. Right? Let's try the next one. Same idea. Right? If we number, we're going to number from the right. So it's 1, 2, 3, 4, 5. So same parachain. So let's go ahead and write that. It's going to be 2-pentene. Does everyone see it's kind of the same idea? There's a double bond. There was 5 carbons. And the 2 tells me that first carbon is part of the double bond. So we always assume the double bond is between the number given and the next highest number. So if it's 2-pentene, it's between carbons 2 and 3. If it's like 8-pentene or 8 some number or some name, it's going to be between carbons 8 and 9, right? So whatever the next number up. Now we just got to name our substituents. So we have a bromine on top. So we change halogens from bromine to bromo, right? Chlorine to chloro. So this one's also on carbon 2, so it's going to be 2-bromo. We have a methyl group, right? Just like we did on the previous one. So it's going to be 4-methyl. And if you remember, we never alphabetized the parent chain, which is this 2-pentene in green, but we alphabetized all the substituents. So the 2-bromo will go first. So I'm just going to be a little bit lazy and steal this bromine. We'll put that there. And let's see, actually, maybe if I move it this way, I'll have a little bit more room. So I'll put the 2-pentene there, 2-bromo. My 4-methyl. And then we can just put a little dash in between each one to separate them. Perfect. So dashes between letters and numbers, commas between 2 numbers. All right, so hopefully it's pretty similar to what you've done before, right? The new wrinkle is double bonds have a higher priority than any of the substituents like methyls, ethyls, or halogens. Right? Doesn't have to be 1, but we got a number from the side that gets to it the fastest. The other thing we'll do, and especially as you move into some of these conjugated systems, we'll start to see things that have multiple double bonds. Right? So we won't name a bunch of these, but I think it's important to just at least be able to recognize what that name means. So if it's a single double bond, we're going to use just the term ene, right? We did before. So it becomes hexene or pentene. If there's multiple, we're going to add the prefix di. Right? So if it's 2 of them, it's di. If it's 3, it's tri. Right? And that makes sense, right? So tri, you think of tricycles. So there's 2. Di, most of us will associate with 2. And so if we just look down at the bottom, we have 1,4-pentadiene. Right? And so if it's 1,4-pentadiene, there's going to be 2 double bonds. Same as before, we just picked the lowest number of the 2. So it's between carbons 1 and 2. So that's why it's 1. And then 4, 5. So that's 4. Same thing on this side. We're going to take our substituent is going to be the methyl group on top. So that's for the methyl. Let's just go ahead and highlight that. So the methyl's here. And then each of the double bonds that gives us our diene. So it's pentadiene because there's 2 of them, and then we just give the number that's associated with them. So we pick the smallest one, so it's 1 and 3. Same thing for this one. We use the term cyclo for a ring, right? So cyclo is going to tell us it's a ring. Remember, in a ring, we can start on any carbon. And so we just start 1, 2, 3, 4. And the same as the previous one, we pick the first number, so it's 1 and then 3. And so 1, 3, cyclopentadiene. Pent tells us there's 5 carbons. Diene, there's 2 double bonds. And the numbers tell us specifically where those double bonds are. Right? So not too bad, kind of all in that same scheme, right? The only difference is that the influx, right? So we just figure out exactly what the group is that we're talking about, and then we put numbers in the front. All right, so one thing we're going to talk about is double bonds, right? And double bonds can be either cis or trans. Right? And so cis means the same side. So if we look at a very simple double bond, we could make something like this, right? And that would be my cis double bond. And this would be my trans. And cis, I would just associate that the two groups are on the same side, right? So that would be a good thing to kind of associate with it. And trans means they're on the opposite side. And what I'm talking about is the groups coming off the double bond. So you see the double bond here. And so these would be my carbon groups. So they're pointing in the same direction, right? They're both pointing down. You could think about the implied hydrogens are both pointing up. Same thing with the double bond here. There's a carbon pointing down, carbon pointing up. So if they're pointing in opposite directions, they're trans. And so one of the things where you've probably actually seen this term before, even before you took any chemistry, is if you look at food labels, if you look at the back, it talks about fats being saturated and unsaturated. And usually if you look at the unsaturated, if you look one level down, it usually tells you the number of trans fats or the amount of trans fats. And so when they're talking about trans fats, that trans literally is talking about this double bond. So they're talking about the double bond in the fats. So whether they're cis fats or trans fats. Last thing about this is we can talk about chiral centers, right? Having 4 different groups coming off of it. But the other stereocenter, right? Stereocenters are this broader term, is anywhere you have a choice between 2 things. So for chiral centers, it's R and S. For double bonds, it's cis or trans. All right, so at any double bond that you can label as cis or trans, you can count that as a stereocenter. So if we're looking at this one, we have a stereocenter here and here. And so these would be examples of trans double bonds. Do you see how this is pointing up and this one's down? Up and down. Same thing if we go through groups here and here. Same thing here, 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 and here. And if we're looking at these, this one would be cis, right? So they're pointing, both carbons are pointing down. The second one would be trans. Cis, and then also cis, right? On this one, both groups are pointing up. Right here, it goes down and then down, but they're pointing the other way, right? So if we're looking at the double bond, we're going to go up from the double bond, down from the double bond, so trans. And then again, cis here, because they're both pointing up from the double bond. All right. So if we're looking at this, this is exactly that, telling us where those double bonds are between carbons 2s and 3s. If you look at it, this is actually the exact same molecule. It's just all the different stereoisomers. So we have all the different combinations. So if we plugged 2N and there's 2 double bonds, right, that we can change between cis and trans. So it'd be 2 to the N is 4. And so there should be 4 possible isomers, right? And that's what this is saying right here, that we have 4 possible isomers between the 2. Okay? And so that's where they come from, right? So we can do this different combination. One last thing, and we're leading this direction. We use the term cis and trans, and it shows up a lot, just like we talked about on food labels. Sometimes it's not super easy to talk about which groups, especially if the groups are different. And so we're going to talk about this nomenclature of E and Z here in a second. All right, so if it doesn't make quite sense why there's these letters in front, it's another way of designating what that double bond looks like. One last thing to be careful about. If we had another molecule, let me do it in blue so it looks different than these, so we know it's a different example. If you have something like this double bond here would be a stereoisomer because it can be cis or trans. If they're on the end, you don't have a cis or trans because the 2 groups coming off that carbon on the end, and let me put it on red, are exactly the same. And so if we switch those 2, we could never make something cis or trans, right? So if it's a double bond on the end of a chain or the exact same stuff coming off that carbon, right? The same 2 groups are coming off of it, then it doesn't count because it doesn't have that cis or trans to it. All right, so you have to be able to designate that double bond as cis or trans, or here in a second when we get to it, E or Z. And if you can't, then it doesn't count as a stereoisomer. So this one would only have 1 stereoisomer in the molecule. All right, so I know in those bigger pictures, sometimes it's a little tough to actually look at what like a cis or trans means. So now that we kind of know that once we find them, we can use the stereoisomers. They actually do matter, right? And so this is part of the thing is if the two groups are on the same side, right? And then on this top, it's the hydrogens, right? So this is going to be cis. They're going to have a little bit different properties, right? And that's what we already know that from fats, right? That if they're trans fats, they behave a little bit different than cis fats, right? And that's why we label them on the food labels. So when you look for something that's cis, it means you're going to take your double bond and they're going to point in the same direction, right? These are generally both pointing down. If it's trans, they're going to point in opposite directions, right? Those carbons are pointing in opposite directions, or if you'd rather look at the hydrogens, right? The hydrogens are pointing in opposite directions. So trans means the two groups are going in opposite direction. Cis means they're going in the same direction, right? So what I would associate with cis is same and trans opposite, right? They're pointing in opposite directions of that double bond. Doesn't matter what direction, just as long as they're pointing opposite. Right? And then what I would associate is they tend to have different properties, right? Melting point is kind of an easy one, or boiling point, because usually you can see a nice measurable difference.